One world currency.
The New World Order.
Those are the roots of trouble.
I imagine that right now you're feeling a bit like Alice, tumbling down the rabbit hole. Let me tell you why you're here. You're here because you know something. What you know you can't explain, but you feel it. You felt it your entire life. That there's something wrong with the world. You don't know what it is, but it's there, like a splinter in your mind, driving you mad. It is this feeling that has brought you to me. This is your last chance. After this, there is no turning back. You take the blue pill, the story ends. You wake up in your bed and believe whatever you want to. You take the red pill, you stay in Wonderland, and I show you how deep the rabbit hole goes. All I'm offering is the truth, nothing more.
For we are opposed around the world by a monolithic and ruthless conspiracy that relies primarily on covert means for expanding its sphere of influence, on infiltration instead of invasion, on subversion instead of elections, on intimidation instead of free choice, on guerrillas by night instead of armies by day. It is a system which has conscripted vast human and material resources into the building of a tightly knit, highly efficient machine that combines military, diplomatic, intelligence, economic, scientific, and political operations. Its preparations are concealed, not published. Its mistakes are buried, not headlined. Its dissenters are silenced, not praised. No expenditure is questioned, no rumor is printed, no secret is revealed. But I am asking your help in the tremendous task of informing and alerting the American people.
And now, welcome to another episode of Down the Rabbit Hole. Here's your host from federaljack.com. It's Popeye.
Ladies and gentlemen, welcome to another live edition. It is October 18th, 2013, the Friday edition of DTRH. The weekend is here, ladies and gentlemen. And as I like to do sometimes on a Friday, we're going to be having like a return to science class, I shall say. Because tonight, just like sometimes I play documentaries about history, or perhaps I go off on rants about certain things in history and I provide different pieces of evidence, today we're going back to class. Except today is going to be science class. Yes, that's right. Science class. People are probably already turning off the radio. What? I don't want to listen to this crap. Wait, hold on. Before you press that button, it's not going to be boring science. It's going to be quantum mechanics and the nature of reality as we know it. I think it'll be very interesting. I'm going to be playing some audio for you, and I'm going to be offering you my analysis of the subject. The reason I want to get into this is because, A, it's something that we deal with every day and we don't even realize it. Our reality is affected by it. But if you have a basic understanding of this stuff, if you have a better basic understanding of quantum mechanics and the nature of reality as it really is, as opposed to the way you think it is, then when I talk about certain weapons or certain technology or the possibility of certain things like interdimensional travel or anything like that, you won't be lost to the conversation. You won't be sitting there going, huh? You'll actually have a base understanding of what I'm talking about and some of the things that I'm talking about with the guests, or if Joe comes on and we talk about it. Unless you have a basic understanding of it, you're going to be kind of lost, and the full level of information and knowledge is going to be somewhat lost to you, because if you don't understand the basics, you're not going to understand anything else. So we're going to go over quantum mechanics tonight. And I've been waiting to do this broadcast for a while because it's hard to get into this subject and make it be interesting to people. Some people like science. Not everybody's a science nerd. Myself, I might be covered in tattoos. I might have owned motorcycles, and I, been in the military and a firefighter. But I'm a nerd. Okay, I'm a big geek when it comes to certain things. And science, I'm a big science nerd. Quantum physics is really interesting. Once you understand it at a base level, like I said, a lot a lot of the things that don't seem very clear to you will become a lot more clear, or a lot clearer, however you want to say it. Anyway, I found I spent about, past 2-3 weeks going through these different documentaries that I have about quantum mechanics, and I've watched myself over the years, and I was trying to find something that was a little user-friendly. And I did. I actually found something that it explains it very simply. It explains it in terms that everybody can understand. You don't have to be a friggin' physicist to understand what they're talking about. And my goal with this whole broadcast tonight is not only to introduce you to quantum mechanics, but also make you think about the nature of reality and how your reality is controlled. Because remember, the powers that shouldn't be understand this. Quantum mechanics isn't new. This stuff has been around for about 100 years. So think about that for a second. If they understand how to control the nature of reality, and they understand the nature of reality, how it really exists and how it really works, and you don't you think that they're going to be able to do things that maybe make them look mystical or have knowledge? Oh my God, how can they do certain things, or how can they know certain things? It's not magic. It's knowledge. They have access to certain things that we don't. So I'm going to try to level the playing field and make everybody a junior grade theoretical physicist tonight. After tonight, I really want you to look into this further. I hope it interests you. I'm not your boss. I'm not your dad or your mom or anything like that. But you know what I mean. I hope this stuff interests you enough that you look into this further and you take this seriously. I mean, quantum mechanics is real, and the reason I'm going at it through quantum mechanics is because I always talk about the nature of reality and how things are controlled, and how they manipulate the powers that shouldn't be, can manipulate the way people see things, right? Well, people a lot of times they go, well, what is it, magic, blah, blah, blah. No, they just understand the nature of reality better than you and me. But not after tonight. We're going to level the playing field a little bit, because that's what it's all about, right? So I hope that this sparks a fire of interest in all of you to learn more about quantum mechanics. And look, this stuff isn't as hard as they try to make it sound like. They make this look really hard and difficult to understand at the same time that they put dumbing down, totally retarded, useless crap on TV like Dancing with the Stars or Monday Night Football or something to that effect. Rather than you want to look into this stuff because it's difficult, you don't want to have to do that. You've just worked. You don't want to deal with that. You've worked all day. You've worked an 8 or 10 or 12-hour shift. You just want to put your feet up and watch something mind-numbing. Well, you know what? Turn off the TV. You can put your feet up, have your glass of wine, have your beer, whatever your poison may be, and sit back and just listen. And I hope this, like I said, I hope this sparks some intrigue in all of you. And this isn't the end-all, be-all. This is going to be the very basic, nutshell version of it. Again, you all have to go research this yourselves. But it's not that hard. The powers that shouldn't be make things look a lot harder than they really are and that they really have to be. Anyway, let's get into it. Here we go. Quantum mechanics. And by the way, it's funny. I found this. It's from Nova. Of all the different documentaries out there about quantum mechanics, the one Nova did was the one that was the simplest to understand. Go figure. Anyway, here we go.
Lying just beneath everyday reality is a breathtaking world where much of what we perceive about the universe is wrong. Physicist and best-selling author Brian Greene takes you on a journey that bends the rules of human experience.
Why don't we ever see events unfold in reverse order? According to the laws of physics, this can happen.
It's a world that comes to light as we probe the most extreme realms of the cosmos, from black holes to the Big Bang, to the very heart of matter itself.
I'm gonna have what he's having.
Here, our universe may be one of numerous parallel realities. The three-dimensional world, merely a mirage. The distinction between past, present, and future, just an illusion.
But how could this be? How could we be so wrong about something so familiar?
Does it bother us? Absolutely.
There's no principle built into the laws of nature that say that theoretical physicists have to be happy.
It's a game-changing perspective that opens up a new world of possibilities. Coming up, the realm of tiny atoms and particles, the quantum realm. The laws here seem impossible.
There's a sense in which things don't like to be tied down to just one location.
Yet they're vital to everything in the universe.
There's no disagreement between quantum mechanics and any experiment that's ever been done.
What do they reveal about the nature of reality? Take a quantum leap on the fabric of the cosmos right now on Nova.
For thousands of years, we've been trying to unlock the mysteries of how the universe works. And we've done pretty well, coming up with a set of laws that describes the clear and certain motion of galaxies and stars and planets. But now we know, at a fundamental level, things are a lot more fuzzy, because we've discovered a revolutionary new set of laws that have completely transformed our picture of the universe. From outer space to the heart of New York City to the microscopic realm, our view of the world has shifted thanks to these strange and mysterious laws that are redefining our understanding of reality. They're the laws of quantum mechanics. Quantum mechanics rules over every atom and tiny particle in every piece of matter, in stars and planets, in rocks and buildings, and in you and me. We don't notice the strangeness of quantum mechanics in everyday life, but it's always there if you know where to look. You just have to change your perspective and get down to the tiniest of scales, to the level of atoms and the particles inside them. Down at the quantum level, the laws that govern this tiny realm appear completely different from the familiar laws that govern big, everyday objects. And once you catch a glimpse of them, you never look at the world in quite the same way. It's almost impossible to picture how weird things can get down at the smallest of scales. But what if you could visit a place like this, where the quantum laws were obvious, where people and objects behaved like tiny atoms and particles? You'd be in for quite a show. Here, objects do things that seem crazy. I mean, in the quantum world, there's a sense in which things don't like to be tied down to just one location, or to follow just one path. It's almost as if things were in more than one place at a time. And what I do here can have an immediate effect somewhere else, even if there's no one there. And here's one of the strangest things of all. If people behave like the particles inside the atom, then most of the time, you wouldn't know exactly where they were. Instead, they could be almost anywhere until you look for them. Hey, I'm gonna have what he's having. So, why do we believe these bizarre laws? Well, for over 75 years, we've been using them to make predictions for how atoms and particles should behave. And in experiment after experiment, the quantum laws have always been right.
It's the best theory we have.
There are literally billions of pieces of confirming evidence for quantum mechanics.
It has passed so many tests of so many bizarre predictions.
There's no disagreement between quantum mechanics and any experiment that's ever been done.
The quantum laws become most obvious when you get down to tiny scales like atoms. But consider this. I'm made of atoms. So are you. So is everything else we see in the world around us. So it must be the case that these weird quantum laws are not just telling us about small things. They're telling us about reality. So how did we discover them? These strange laws that seem to contradict much of what we thought we knew about the universe. Not long ago, we thought we had it pretty much figured out. The rules that govern how planets orbit the sun. How a ball arcs through the sky. How ripples move across the surface of a pond. These laws were all spelled out in a series of equations called classical mechanics, and they allowed us to predict the behavior of things with certainty. It all seemed to be making perfect sense. Until about 100 years ago, when scientists were struggling to explain some unusual properties of light. For example, the kind of light that glowed from gases when they were heated in a glass tube. When scientists observed this light through a prism, they saw something they'd never expected.
If you heated up some gas and looked at it through a prism, it formed lines. Not the continuous spectrum that you see projected by a piece of cut glass on your table, but very distinct lines.
It wouldn't give out a smeared, kind of complete rainbow of light. It would give out sort of pencil beams of light at very specific colors.
And it was something of a mystery how to understand what was going on.
An explanation for the mysterious lines of color would come from a band of radical scientists who at the beginning of the 20th century were grappling with the fundamental nature of the physical world. And some of the most startling insights came from the mind of Niels Bohr, a physicist who loved to discuss new ideas over ping pong. Bohr was convinced that the solution to the mystery lay at the heart of matter, in the structure of the atom. He thought that atoms resembled tiny solar systems, with even tinier particles called electrons orbiting around a nucleus, much the way the planets orbit around the sun. But Bohr proposed that unlike the solar system, electrons could not move in just any orbit. Instead, only certain orbits were allowed.
And he had a really surprising and completely counter-physical idea, which was that there were definite states, fixed orbits that these electrons could have, and only those orbits.
Bohr said that when an atom was heated, its electrons would become agitated and leap from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths, and that's why atoms produce very specific colors. This is where we get the phrase quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. But that's not what we see in the laboratory. You see very sharp reds and very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
What made the quantum leap so surprising was that the electron goes directly from here to there, seemingly without moving through the space in between. It was as if Mars suddenly popped from its own orbit out to Jupiter. Bohr argued that the quantum leap arises from a fundamental and fundamentally weird property of electrons and atoms, that their energy comes in discrete chunks that cannot be subdivided, specific minimum quantities called quanta. And that's why there are only discrete, specific orbits that electrons can occupy.
An electron had to be here or there and simply nowhere in between. And that's like nothing we experience in everyday life.
Think of your daily life. When you eat food, you think your food is quantized? Do you think that you have to take a certain amount of minimum food? Food is not quantized. But the energy of electrons in an atom are quantized. that is very mysterious, why that is.
As mysterious as it might be, the evidence quickly mounted showing that Bohr was right. Electrons followed a different set of rules than planets or ping pong balls. Bohr's discovery was a game changer. And with this new picture of the atom, Bohr and his colleagues found themselves on a collision course with the accepted laws of physics. The quantum leap was just the beginning. Soon Bohr's radical views would bring him head-to-head with one of the greatest physicists in history. Albert Einstein was not afraid of new ideas. But during the 1920s, the world of quantum mechanics began to veer in a direction Einstein did not want to go. A direction that sharply diverged from the absolute definitive predictions that were the hallmark of classical physics.
If you asked Einstein or other physicists at the time what it was that distinguished physics from all kind of flaky speculation, they would have said it's that we can predict things with certainty. And quantum mechanics seemed to pull the rug out from under that.
One test in particular, which would come to be known as the double slit experiment, exposed quantum mysteries like no other. If you're looking for a description of reality based on certainty, your expectations would be shattered. We can get a pretty good feel for the double slit experiment and how dramatically it alters our picture of reality by carrying out a similar experiment, not on the scale of tiny particles, but on the scale of more ordinary objects, like those you'd find here in a bowling alley. But first, I need to make a couple of adjustments to the lane. You'd expect that if I roll a few of these balls down the lane, they'll either be stopped by the barrier or pass through one or the other slit and hit the screen at the back.
What he's talking about is, for visual, so you guys can have an understanding, is if you're looking down a bowling alley, if you would imagine where the pins were, there's a screen in front of the pins, like a black screen. And in between the screen and where you're standing at the other end of the alley there is a barrier that pops up. And it's a steel barrier, and in that barrier there are two slits. He's giving it's a physical representation of the slit experiment. I just want you to have that visual in your head now that because you can't obviously see the documentary, right? So now you have that visual in your head of a screen, a black screen at the end of the alley where the pins would be, and in between him and that screen is a barrier with two slits. Now let's listen to what he has to say.
And in fact, that's just what happens. Those balls that make it through always hit the screen directly behind either the left slit or the right slit.
The double slit experiment was much like this, except instead of bowling balls, you use electrons, which are billions of times smaller.
You can picture them like this.
And the slits, when he says picture them like this, what you see are the atoms pop up in where the bowling ball retrieval machine would pick, where it kind of spits it out and they line up. And he's got them. They're obviously small. They're for visual representation, they're about the size of a softball in his hand. And then the slits are obviously much narrower. So now you have an idea. The same thing. You have the screen at the end and the barrier with the two slits, but now the slits aren't wide enough to allow a bowling ball to go through. They're only wide enough to allow perhaps a softball to go through.
What happens if I throw a bunch of these balls? When electrons are hurled at the two slits, something very different happens on the other side. Instead of hitting just two areas, the electrons land all over the detector screen, creating a pattern of stripes, including some right between the two slits, the very place you'd think would be blocked. So, what's going on? Well, to physicists, even in the 1920s, this pattern could mean only one thing. Waves. Waves do all kinds of interesting things. Things that bowling balls would never do. They can split. They can combine. If I sent a wave of water through the double slits, it would split in two, and then the two sets of waves would intersect. Their peaks and valleys would combine, getting bigger in some places, smaller in others, and sometimes they cancel each other out. With the height of the water corresponding to brightness on the screen, the peaks and valleys would create a series of stripes and what's known as an interference pattern. So, how could electrons, which are particles, form that pattern? How could a single electron end up in places a wave would go?
Particles are particles, waves are waves. How can a particle be a wave? Unless you give up the idea that it's a particle and think, aha, this thing that I thought was a particle was actually a wave. A wave in a...
I'm going to pause it right there because the break's sneaking up. I know. You're all scratching your heads right now going, what? No. Trust me. It'll sink in, I promise. It'll all come together by the end of the broadcast. Quantum mechanics and the nature of reality. Stay tuned. Don't go anywhere. We are back, ladies and gentlemen. Quantum mechanics and the nature of reality. I told you science class can be fun. And I'm sure there will be some of you that are going to go, what? I don't understand any of this. This stuff's making my brain hurt. Just, again, go get a glass of wine, sit back. And if you're in a state where it's quote-unquote legal, even if you're not, whatever. Spark a joint, do whatever you got to do to sit and get your brain thinking. Don't drink too much beer because that just turns you into an idiot. But do whatever you got to do. Sit back and just listen to the information, okay? Listen to what's coming out of the speakers and let your brain hear it. Don't try to put up any preformed thoughts or anything. Just put all that stuff to the side and just listen. And then after the broadcast is over, you can find it on YouTube, and I'll find the link during the broadcast, and I'll drop it into the chat room over on federaljack.com and Truth Frequency Radio. There's a listen live page. There's a chat room over on Truth Frequency, and if you go over to Federal Jack, there's a listen live page. It's the same chat, so either way, that's two portals you can get to go to the Truth Frequency network chat, and that's the one I use for the show, and that's where I will be putting the link to the full documentary. The documentary is titled Quantum Mechanics, The Fabric of the Cosmos, which is also the title of the book of the physicist who's doing the bulk of the explanation to you all. And everybody else that you hear commenting throughout this whole thing are all physicists as well. So let's get back to it. I'm going to pick it up right where we left off. He was doing the double slit experiment, and he had just finished explaining how when they throw, when they were testing this, in lieu of the bowling ball, they switched the bowling ball up with electrons. I said atoms before, by the way, and my brain was doing 6 different things. I apologize. It was electrons. He was explaining the double slit experiment and how if you rolled the bowling balls down the alleyway, they would only appear where the holes were, or where the slits were in this barrier. That the holes would line up with the slits in the barrier that was in the middle of the bowling alley. But the electrons were appearing even in spots behind where this barrier would have been. So they weren't obviously traveling in a straight line, which meant they were traveling in a wave pattern. And then they were getting into how could a solid particle be a wave, because a particle is not a wave and a wave is not a particle. And that's where I had to cut it off when we went to break. So I know this all, again, this sounds a little weird. Go watch this, listen to the broadcast, and go watch the documentary again. It'll help give a visual to it. And then go check out movies like What the Bleep Do We Know? And there was a sequel to it, like I think it's Further Down the Rabbit Hole, What the Bleep Do We Know More, or something like that. I'm wrecking the title. But it's What the Bleep Do We Know? And then there's this like a compendium secondary part to it. And those are good documentaries to watch, too, for the uninitiated into quantum mechanics, because it'll help ease you into it as well. This is a field, a science that it's going to take a little bit to understand. Because remember, it's actually taking everything that we've been taught by classical science class and in high school and by the mind-altering education system. It's actually taking it and turning it on its head, because they didn't even, at least when I was in school, they didn't talk about quantum mechanics. I didn't find out about this stuff until after I graduated high school and I got out, and I continued to want to educate myself, and I stumbled upon this stuff. So let's get right back into it. Like I said, they were talking about particle is not a wave, and a wave is not a particle.
An ocean? That's not a particle. The ocean is made out of particles, but the waves in the ocean are not particles. And rocks are not waves. Rocks are rocks. So a rock is an example of a particle. An ocean wave is an example of an ocean wave. And now somebody's telling you a rock is like an ocean wave. What?
Back in the 1920s, when a version of this experiment was first done, scientists struggled to understand this wavy behavior. Some wondered if a single electron, while in motion, might spread out into a wave. And the physicist Erwin Schrödinger came up with an equation that seemed to describe it.
Schrödinger thought that this wave was a description of an extended electron, that somehow an electron got smeared out, and it was no longer a point, but was like a mush.
There was a lot of argument about exactly what this represented.
Finally, a physicist named Max Born came up with a new and revolutionary idea for what the wave equation described. Born said the wave is not a smeared out electron or anything else previously encountered in science. Instead, he declared it's something that's really peculiar, a probability wave. That is, Born argued that the size of the wave at any location predicts the likelihood of the electron being found there.
Where the wave is big, that's not where most of the electron is. That's where the electron is most likely to be.
And that's just very strange, right? So the electron on its own seems to be a jumble of possibilities.
You're not allowed to ask, where is the electron right now? You are allowed to ask, if I look for the electron in this little particular part of space, what is the likelihood I will find it there? I mean, that bugs anyone, anytime.
As weird as it sounds, this new way of describing how particles like electrons move is actually right. When I throw a single electron, I can never predict where it will land. But if I use Schrödinger's equation to find the electron's probability wave, I can predict with great certainty that if I throw enough electrons, then say 33.1% would end up here, 7.9% would end up there, and so on. These kinds of predictions have been confirmed again and again by experiments. And so the equations of quantum mechanics turn out to be amazingly accurate and precise, so long as you can accept that it's all about probability. If you think that probability means you're reduced to guessing, the casinos of Las Vegas are ready to prove you wrong. Try your hand at any one of these games of chance, and you can see the power of probability. Let's say I place a $20 bet on number 29 here at the roulette table. The house doesn't know whether I'll win on this spin, or the next, or the next.
1.
But it does know the probability that I'll win. In this game, it's 1 in 38.
21. 29.
So, even though I may win now and then, in the long run, the house always takes in more than it loses. The point is, the house doesn't have to know the outcome of any single card game, roll of the dice, or spin of the roulette wheel. Casinos can still be confident that over the course of thousands of spins, deals, and rolls, they will win. And they can predict with exquisite accuracy exactly how often. According to quantum mechanics, the world itself is a game of chance, much like this. All the matter in the universe is made of atoms and subatomic particles that are ruled by probability, not certainty.
At base, nature is described by an inherently probabilistic theory. And that is highly counterintuitive and something which many people would find difficulty accepting.
One person who found it difficult was Einstein. Einstein could not believe that the fundamental nature of reality at the deepest level was determined by chance.
And this is what Einstein could not accept. Einstein said, God does not throw dice. He didn't like the idea that we couldn't with certainty say this happens or that happens.
But a lot of other physicists weren't so put off by probability, because the equations of quantum mechanics gave them the power to predict the behavior of groups of atoms and tiny particles with astounding precision. Before long, that power would lead to some very big inventions. Lasers, transistors, the integrated circuit, the entire field of electronics.
If quantum mechanics suddenly went on strike, every single machine that we have in the US almost would stop functioning.
The equations of quantum mechanics will help engineers design microscopic switches that direct the flow of tiny electrons and control virtually every one of today's computers, digital cameras, and telephones.
All the devices that we live on, diodes, transistors, just to form the basis of information technology, the basis of daily life in all sorts of ways. They work. And why do they work? They work because of quantum mechanics.
I'm tempted to say that without quantum mechanics, we'd be back in the dark ages. I guess more accurately, without quantum mechanics, we'd be back in the 19th century. Steam engines, telegraph signals.
Quantum mechanics is the most successful theory that we physicists have ever discovered. And yet we're still arguing about what it means, what it tells us about the nature of reality.
In spite of all its triumphs, quantum mechanics remains deeply mysterious. It makes all this stuff run, but we still haven't answered basic questions raised by Albert Einstein all the way back in the 1920s and 30s. Questions involving probability and measurement, the act of observation. For Niels Bohr, measurement changes everything. He believed that before you measured or observed a particle, its characteristics were uncertain. For example, an electron in the double slit experiment. Before the detector at the back pinpoints its location, it could be almost anywhere with a whole range of possibilities. Until the moment you observe it. And only at that moment will the location's uncertainty disappear. According to Bohr's approach to quantum mechanics, when you measure a particle, the act of measurement forces the particle to relinquish all of the possible places it could have been and select one definite location where you find it. The act of measurement is what forces the particle to make that choice. Niels Bohr accepted that the nature of reality was inherently fuzzy, but not Einstein. He believed in certainty, not just when something is measured or looked at, but all the time. As Einstein said, I like to think the moon is there, even when I'm not looking at it.
This is something that you've heard me talk about in conversations when I've brought up quantum mechanics before. In fact, I had this conversation with Chris and Cherie Gio. One of the last times they were on when we got into the topic of the nature of reality. And one of the things that we brought up is, does anything actually exist behind you? If you're not looking, is it really there? And people say, what do you mean? Like, if you don't see the moon in the sky, if I turn my head and I'm not looking, is it really there, or is it only there because I physically manifest it when I see it, when I look up, because I expect it to be there? I mean, these are deep questions, but this is the kind of thing that quantum mechanics forces you to look at, because by understanding what he just said about it could be anywhere, the electron, and the only time that it actually shows up where it is when you go to measure it. You figure the probability of the greatest probability is it'll end up here, and when you go to pick that spot, that the electron appears there. So what does that tell you? Well, if you understand this a little bit, you'll understand that has a lot to do with choice, right? Is this all starting to connect a little bit? Like you choose to look in that, the probability tells you that that's where it's going to be, and when you look, that's where the electron appears, right? So that when you're looking, when you're measuring, as they say, right, you're gauging it, whatever, that's when it appears there. So if that kind of plays with our whole the way we look at reality, or is the coffee cup that's on my desk that I'm holding in my hand right now in my left hand, is it there all the time, or is it only there because I know the coffee cup is there, and in my mind, I put the coffee in it, and before I came on air, and I put the coffee cup on my desk. Do you understand? Like, thoughts create reality is what I'm trying to tell you. So you can see how the comment and the idea of thoughts creating reality, somebody might say, oh, there's no evidence to back that up. Quantum physics, quantum mechanics is telling you exactly that.
That's what Einstein was so upset about. Do we really think the reality of the universe rests on whether or not we happen to open our eyes? That's just bizarre.
Einstein was convinced something was missing from quantum theory, something that would describe all the detailed features of particles, like their locations, even when you were not looking at them. But at the time, few physicists shared his concern.
And Einstein just thought it was giving up on the job of the physicist. It wasn't bad physics per se, it just was totally incomplete.
That's Einstein's refrain. Quantum mechanics is not incorrect, it's insofar as it goes, but it's incomplete. It doesn't capture all of the things that can be said or predicted with certainty.
Despite Einstein's arguments, Niels Bohr remained unmoved. When Einstein repeated that God does not play dice, Bohr responded, "Stop telling God what to do." But in 1935, Einstein thought he'd finally found the Achilles heel of quantum mechanics. Something so strange, so counter to all logical views of the universe, he thought it held the key to proving the theory was incomplete. It's called entanglement.
The most bizarre, the most absurd, the most crazy, the most ridiculous prediction that quantum mechanics makes is entanglement.
Entanglement is a theoretical prediction that comes from the equations of quantum mechanics. Two particles can become entangled if they're close together and their properties become linked. Remarkably, quantum mechanics says that even if you separated those particles, sending them in opposite directions, they could remain entangled, inextricably connected. To understand how profoundly weird this is, consider a property of electrons called spin. Unlike a spinning top, an electron spin, as with other quantum qualities, is generally completely fuzzy and uncertain until the moment you measure it. And when you do, you'll find it's either spinning clockwise or counterclockwise. It's kind of like this wheel. When it stops turning, it will randomly land on either red or blue. Now imagine a second wheel. If these two wheels behave like two entangled electrons, then every time one landed red, the other is guaranteed to land on blue. And vice versa. Now, since the wheels are not connected, that's suspicious enough. But the quantum mechanics embraced by Niels Bohr and his colleagues went even further, predicting that if one of the pair were far away, even on the moon, with no wires or transmitters connecting them. Still, if you look at one and find red, the other is sure to be blue. In other words, if you measured a particle here, not only would you affect it, but your measurement would also affect its entangled partner, no matter how distant. For Einstein, that kind of weird long-range connection between spinning wheels or particles was so ludicrous, he called it spooky. Spooky action at a distance.
When you have one particle here and one particle there, and they are separated enough that there is no signal able to allow them to communicate, and they still seem to be talking to each other, then is a big mystery.
What's surprising is that when you make a measurement of one particle, you affect the state of the other particle. You change its state.
There's no forces or pulleys or, telephone wires. There's nothing connecting those things, right? How could my choice to act here have anything to do with what happens over there?
So there's no way they can communicate with each other. So it is completely bizarre.
Einstein just could not accept that entanglement worked this way, convincing himself that only the math was weird, not reality. He agreed that entangled particles could exist, but he thought that there was a simpler explanation for why they were linked that did not involve a mysterious long-distance connection. Instead, he insisted that entangled particles were more like a pair of gloves. Imagine someone separates the two gloves, putting each in a case. Then that person delivers one of those cases to me and sends the other case to Antarctica. Thanks. Before I look inside my case, I know that it has either a left hand or a right hand glove. And when I open my case, if I find a left hand glove, then at that instant, I know the case in Antarctica must contain a right-hand glove, even though no one has looked inside. There's nothing mysterious about this. Obviously, by looking inside the case, I've not affected either glove. This case has always had a left-hand glove, and the one in Antarctica has always had a right-hand glove. That was set from the moment the gloves were separated and packed away. Now, Einstein thought that exactly the same idea applies to entangled particles. Whatever configuration the electrons are in must have been fully determined from the moment that they flew apart.
Einstein comes and says, look, if there is this strong correlation, it means that the direction of the spins were already determined before you do the measurement.
So, who was right? Bohr, who championed the equations that said that particles were like spinning wheels that could immediately link their random results even across great distances, or Einstein, who believed there was no spooky connection, but instead everything was decided well before you looked. Well, the big challenge in figuring out who is right, Bohr or Einstein, is that Einstein is saying a particle, say, has a definite spin before you measure it. How do you check that, you say to Einstein? He says, well, measure it, and you'll find the definite spin. Bohr would say, but it's the act of measurement that brought that spin to a definite state. No one knew how to resolve the problem. So the whole question came to be considered philosophy, not science. In 1955, Einstein died, still convinced that quantum mechanics offered, at best, an incomplete picture of reality. In 1967, at Columbia University, Einstein's mission to challenge quantum mechanics was taken up by an unlikely recruit. John Clauser was on the verge of earning a PhD in astrophysics. The only thing standing in his way was his grade in quantum mechanics.
When I was still a graduate student, try as I might, I could not understand quantum mechanics.
Clauser was wondering if Einstein might be right when he made a life-altering discovery. It was an obscure paper by a little-known Irish physicist named John Bell. Amazingly, Bell seemed to have found a way to break the deadlock between Einstein and Bohr and show once and for all who was right about the universe.
I was convinced that the quantum mechanical view was probably wrong.
Reading the paper, Clauser saw that Bell had discovered how to tell if entangled particles were really communicating through spooky action, like matching spinning wheels, or if there was nothing spooky at all, and the particles were already set in their ways, like a pair of gloves. What's more, with some clever mathematics, Bell showed that if spooky action were not at work, then quantum mechanics wasn't merely incomplete, as Einstein thought. It was wrong.
I came to the conclusion that, my God, this is one of the most profound results I've ever seen.
Bell was a theorist, but his paper showed that the question could be decided if you could build a machine that created and compared many pairs of entangled particles.
Bell turned the question into an experimental question.
It wasn't just going to be about philosophy or trading pieces of paper.
And the experiment that he envisioned could be done.
You could really set up an actual experiment to force the issue.
I'm going to pause it right there because we got a break coming up in about a minute. And I don't want you to lose the context of it, going into the break and then coming back on the other side in 3 minutes. In fact, what I'm going to do is, so people get the full context of the next piece here, I'm going to actually rewind it about 2.5 minutes to the beginning of where they start talking about Bell and his work and what it led to, and then where we are now. So you get the full context. It's important to understand this stuff. I know it might seem a little tedious, but I promise, by the end of the broadcast, you will have a basic understanding that reality and science and everything that we've been taught is not complete. I won't say it's all a lie. Some of it's a lie, but it's not complete and accurate.
This is Sparta!
By looking into quantum physics and quantum mechanics, it will help you understand certain things a lot better. Again, I'm trying to level the playing field. That's the goal for tonight's broadcast. I'll see you in 3 minutes. Don't go anywhere. We'll be right back. Ladies and gentlemen, we are back with hour number 2 here on tonight's live edition of Down the Rabbit Hole. I am your host, Popeye from FederalJack.com. It is October 18th, 2013, and here on tonight's Friday edition, I am talking about quantum mechanics and the nature of reality. And going through it, I've been trying to... I've been letting the audio pretty much play. I only interrupted here or there to interject something to show you how it connects. Make the connection a little bit simpler for you. But again, you're not going to walk away from this broadcast tonight like a PhD and understand all this stuff. At the most, you're going to have a basic understanding of it, but there's going to be so many more questions than answers, and that's good because those questions are what I want you to go research, and I maybe that'll be the force that urges you. Maybe this will, literally spark a fire of intrigue in your minds. That's the whole point of me doing these broadcasts, right? So, for lack of time, because we only have another hour here, and I want to finish this, and there's so much that I want to add to it and interject myself. So, and I'm trying to refrain from interrupting it too much because I don't want to confuse you guys. And what I did was, like I said last hour, what I did was I rewound it a few minutes to pick it up so you get the full context of the second half of it. Because the first half we've kind of gotten the somewhat of the basics and very, very basics, a very, very basic understanding of quantum mechanics. But now they were talking about, when we left off, they were talking about Einstein and Niels Bohr had this difference of opinion that neither one of them could solve. Bohr thought that two entangled particles acted the way they did because of spooky action, some unforeseen connection, and Einstein said, no, it's just, that's not the way it works. We just don't understand quite how it works, and he thought it was already determined. It was already a predetermined thing. So I rewound it a few minutes to pick it up right there, because then it gets into Bell and his work and a bunch of other things. And like I said, I wanted you to have the full context. So I expect a lot of you to walk away from this going like, huh, tonight? Go watch, again, the movies. What is it? What the Bleep Do We Know? There's 2 of them. And then the documentary that I'm playing, and I urge you to go watch it again yourself. And then, read books. Read as many books as you can on this. Sometimes maybe for people that the books might be dry and confusing, sometimes the documentaries are equally as good. I don't personally. People have asked me what I think Michio Kaku. Do I like him as a theoretical physicist? Not really, but it doesn't mean that the information that he is in some of these documentaries and some of the stuff that he does talk about, in at least regards to quantum physics and stuff, is accurate. Him being a shill for the New World Order, scumbag elites. Well, that's a different thing, but. Anyway, I digress. I want to get back to the film. Quantum Mechanics, Fabric of the Cosmos. And like I said, we're picking up with the difference of opinion between Niels Bohr and Einstein in regards to quantum entanglement.
The big challenge in figuring out who is right, Bohr or Einstein, is that Einstein is saying a particle, say, has a definite spin before you measure it. How do you check that, you say to Einstein? He says, well, measure it, and you'll find the definite spin. Bohr would say, but it's the act of measurement that brought that spin to a definite state. No one knew how to resolve the problem. So the whole question came to be considered philosophy, not science. In 1955, Einstein died, still convinced that quantum mechanics offered, at best, an incomplete picture of reality. In 1967, at Columbia University, Einstein's mission to challenge quantum mechanics was taken up by an unlikely recruit. John Clauser was on the verge of earning a PhD in astrophysics. The only thing standing in his way was his grade in quantum mechanics.
When I was still a graduate student, try as I might, I could not understand quantum mechanics.
Clauser was wondering if Einstein might be right when he made a life-altering discovery. It was an obscure paper by a little-known Irish physicist named John Bell. Amazingly, Bell seemed to have found a way to break the deadlock between Einstein and Bohr and show once and for all who was right about the universe.
I was convinced that the quantum mechanical view was probably wrong.
Reading the paper, Clauser saw that Bell had discovered how to tell if entangled particles were really communicating through spooky action, like matching spinning wheels, or if there was nothing spooky at all, and the particles were already set in their ways, like a pair of gloves. What's more, with some clever mathematics, Bell showed that if spooky action were not at work, then quantum mechanics wasn't merely incomplete, as Einstein thought. It was wrong.
I came to the conclusion that, my God, this is one of the most profound results I've ever seen.
Bell was a theorist, but his paper showed that the question could be decided if you could build a machine that created and compared many pairs of entangled particles.
Bell turned the question into an experimental question.
It wasn't just going to be about philosophy or trading pieces of paper.
And the experiment that he envisioned could be done.
You could really set up an actual experiment to force the issue.
Clauser set about constructing a machine that would finally settle the debate.
Now, I was just this punk graduate student at the time. This really seemed like, wow. There's always the slim chance that you will find a result that will shake the world.
Clauser's machine could measure thousands of pairs of entangled particles and compare them in many different directions. As the results started coming in, Clauser was surprised and not happy.
I kept asking myself, what have I done wrong? What mistakes have I made in this?
Clauser repeated his experiments, and soon French physicist Alain Aspect developed some even more sophisticated tests, with one going to the heart of the Einstein-Bohr debate. In Aspect's test, the only way that measuring one of the particles could directly influence the other would be for a signal to travel between them faster than the speed of light, something Einstein himself had shown impossible. The only remaining explanation was spooky action, and so Aspect's experiment removed virtually all doubt.
Quantum mechanics is true even in the most mysterious and the most weird situations.
The results of these experiments are truly shocking. They prove that the math of quantum mechanics is right. Entanglement is real. Quantum particles can be linked across space. Measuring one thing can in fact instantly affect its distant partner, as if the space between them didn't even exist. The one thing that Einstein thought was impossible, spooky action at a distance, actually happens.
I was, again, very saddened that I had not overthrown quantum mechanics, because I still had, and to this day, still have great difficulty in understanding it.
That is the most bizarre thing of quantum mechanics. It is impossible to even comprehend. Don't even ask me why. Don't ask me which you're going to, how it works, because it's an illegal question. All we can say is that is apparently the way the world ticks.
So if we accept that the world really does tick in this bizarre way, could we ever harness the long-distance spooky action of entanglement to do something useful? Well, one dream has been to somehow transport people and things from one place to another without crossing the space in between. In other words, teleportation.
Get me aboard. Energize. Energize.
Star Trek has always made beaming or teleporting look pretty convenient. It seems like pure science fiction, but could entanglement make it possible? Remarkably, tests are already underway here on the Canary Islands off the coast of Africa.
We do the experiments here on the Canary Islands because you have 2 observatories, and after all, it's a nice environment.
Anton Zeilinger is a long way from teleporting himself or any other human. But he is trying to use quantum entanglement to teleport tiny individual particles. In this case, photons, particles of light. He starts by generating a pair of entangled photons in a lab on the island of La Palma. One entangled photon stays on La Palma, while the other is sent by laser-guided telescope to the island of Tenerife, 89 miles away. Next, Zeilinger will bring in a third photon, the one he wants to teleport, and have it interact with the entangled photon on La Palma. The team will study the interaction, comparing the quantum states of the 2 particles. And here's the amazing part. Because of spooky action, the team will be able to use that comparison to transform the entangled photon on the distant island into an identical copy of that third photon. It will be as if the third photon teleported across the sea, without traversing the space between the islands.
Sort of extract the information carried by the original and make a new original there.
Using this technique in other locations, Zeilinger has successfully teleported dozens of particles. But could this go even further? Since we're made of particles, could this process make human teleportation possible one day?
Welcome to New York City.
Let's say I want to get to Paris for a quick lunch. Well, in theory, entanglement might someday make that possible. Here's what I'd need. A chamber of particles here in New York that's entangled with another chamber of particles in Paris.
Right this way, Mr. Green.
I would step into a pod that acts sort of like a scanner or a fax machine. While the device scans the huge number of particles in my body, more particles than there are stars in the observable universe, it's jointly scanning the particles in the other chamber, and it creates a list that compares the quantum state of the two sets of particles. And here's where entanglement comes in. Because of spooky action at a distance, that list also reveals how the original state of my particles is related to the state of the particles in Paris. Next, the operator sends that list to Paris. There, they use the data to reconstruct the exact quantum state of every single one of my particles. And a new me materializes. It's not that the particles traveled from New York to Paris. It's that entanglement allows my quantum state to be extracted in New York and reconstituted in Paris, down to the last particle.
Now I'm going to pause it there for a second. I want to theorize something of my own, and I'm sure if I've thought about this, then people much smarter than me have thought about it. I mean, I'm a pretty smart guy, but there's physicists and scientists that are way smarter than me, and I'm sure they've already thought of this if I have. Think about this for a second. If you get transported from one spot to another, right, and they can literally reconstitute your whole body, pretty much the computer would have a roadmap, as it were, an instruction manual of what you were, the exact composite makeup of every cell in your body, a blueprint. And they could remake you as long as they had these two empty hollow chambers of, I guess standard regular particles, and then they could, they'd copy you and make a new copy of you, and you would be, quote unquote, transported. Now, getting around the whole idea of your soul and everything else. Okay, aside from that, think about something that you could look at health-wise. If the computer was smart enough to map your entire body, obviously, then you could probably take that smart computer and program it that if you had, say, a tumor in your body, that they could literally just transport you from one side of the room in a hospital to the other, and when you stepped into the one transportation chamber, you would be sick with your cancer, and when you stepped out of the tube on the other side, you wouldn't have the disease anymore or that illness, because they could literally program the computer to leave that out, not remanifest that. Find out the exact, DNA code or structure or whatever, the exact blueprint of that. If you can do it of the entire body, I'm sure the next step would be each individual piece, right? So then you could, technically, you would be able to, beam, like I said, say someone had cancer of, they had a tumor in their brain, we'll say. They have a big brain tumor. And they're laying in, they're in the hospital bed or whatever. You could wheel them into the tube, have the computer literally take a blueprint of the entire body, and then single out the tumor, and reanimate the new body without the tumor there. You could even, I'm sure there might be the problem of, will there be the space left by the tumor not being there? Well, I'm sure you could figure out a way to, if you could figure, if we're already at that step, I'm sure you could figure out a way to fix that problem too. I'm sure by that point, if we're already teleporting things, we're a step ahead of the game. But it's just an interesting idea. According to quantum mechanics, that's how, and they've done it already with experiments with, a single particle. So if theoretically they could do teleportation like that, again, not only does it open up the realm of possibilities with travel, like they talked about, but again, my first thing I thought of when I saw this is when I first saw the documentary, and every time I watch it, it's this. Every time I get to this spot, it's the same thought I have. That think about the implications for health. If you had. And it doesn't work with everything. It's not like a cure-all, but for something like cancer or something like that, that takes a physical manifestation inside of your physical body, not so much a condition that would cause something to, like your blood pressure to drop, or a weak heart and having a heart attack, but a physical tumor or something. You could. Theoretically, right? If we're talking about teleportation here, theoretically, you could program that computer to exclude that from, the rebuilding inside of the tube, and the person would come out technically a healthy individual without that cancerous tumor or cancer or whatever inside their body. So it's just an interesting thought, and again, it opens up the realm of possibilities for travel, like you wouldn't believe. Think about it. Think about being able to travel from Paris to New York that fast. It would make things much easier. Communication between human beings. It would open up a whole level of things, a whole level of things that they don't want. The powers that shouldn't be don't want. Imagine war. You wouldn't need to have wars, because we could just, we wouldn't have to be chasing each other for all sorts of, maybe the precious metals to make the equipment, but no oil at least, because I'm sure they wouldn't run the particle accelerator, like I'm sure CERN's not run off of gasoline. I'm sure they don't go over to the local petrol station and fill up gas cans for CERN. I know it uses a lot of electricity, but that would also force you to maybe make your own type of electrical plant on the facility on the location, perhaps geothermal, perhaps. I don't know. Here I am trying to solve problems. Anyway, back to quantum physics.
Bonjour, Monsieur Green.
Hi there. So here I am in Paris, an exact replica of myself, and I better be, because measuring the quantum state of all my particles in New York has destroyed the original me.
It is absolutely required in the quantum teleportation protocol that the thing that is teleported is destroyed in the process. And, that does make you a little anxious. I guess you would just end up being a lump of neutrons, protons, and electrons. You wouldn't look too good.
Now, we are a long way from human teleportation today, but the possibility raises a question. Is the Brian Greene who arrives in Paris really me? Well, there should be no difference between the old me in New York and the new me here in Paris. And the reason is that, according to quantum mechanics, it's not the physical particles that make me me. It's the information those particles contain. And that information has been teleported exactly.
And by the way, Dave admitted that DNA is more or less like a thumb drive, a flash drive of information with our personal, each of us, our personal chemical makeup. It's also a sending and receiving antenna, hence the shape. It's a spiral and a shaft. I could go into this. It's a round antenna, and it's a straight up and down antenna, vertical antenna. One's better at sending out, and one's better at receiving. The vertical is a good receiver. The cylindrical aspect of it is also a good sender, or if you will, whatever you want to call it. And it also, science is playing with, you can go look this up, that they're looking at using DNA to store information. So obviously the DNA itself, the strand, is more so a physical thumb drive of our data. And again, that's what gave me the idea about, well, if that's the case, if it's a blueprint, ones and zeros, right, our matrix code, our coding, what happens if you have a website that has a bad piece of code when a hacker goes and installs malware on it, right? And you have flash pop-ups or redirects on your site now. Well, what do you have to do if you're the coder, or what does your IT person do if you have an IT guy to do that stuff? what do? Well, they go line by line in the code, and they find the bad code, and they remove it. And what happens? The site goes back to functioning properly, and everything works hunky-dory, right? And then you can build up protections so that the next time the hackers come and try to hack you or whatever, they can't put that malicious code into your website. Well, what happens if our bodies are the same way and we just don't realize that? Maybe that's how it really works, right? Think about that. If you can understand the coding of your physical body, which is what's inside of your DNA, if they can map that and transport you, teleport you, whatever, from one spot to the next, why couldn't they figure out the DNA mapping of that, the cancerous tumor or whatever else? I mean, like I said, it's not going to fix everything, but certain things, why couldn't they figure out the DNA mapping of that and redo it? Maybe you have a bad organ, and maybe they can map the organ, and they can transport you and teleport you, and they can figure out a way to, if the coding is messed up, clean the code up so when they make the new you, the code is fixed. I mean, you could think about the health implications, the lengthening of life. I mean, this is the real deal. And again, quantum mechanics, all this stuff has been around for a very long time, at least 100 years. Now, I'm sure if you went to college and you studied, maybe you got a degree in physics or something, you were exposed to this. And you might have, even if you weren't in a physics major or something, maybe if you majored in something else, you might have been exposed to this. But how many people go to college after high school? Because they certainly don't teach, maybe they do now, but they certainly didn't when I was in high school. They weren't teaching quantum mechanics. They didn't teach us this stuff. I'm sure my science teacher knew about it, but the discussion of quantum mechanics never came up. Although things might be a little different nowadays because, I mean, it's more mainstream. YouTube, kids will hear a radio show like this or see the Nova documentary. I mean, it would be a good documentary just to show in your class. That's why I like I said, I spent a couple weeks trying to find some stuff to play for you guys, help simplify some of this information down. And again, this is not an end-all, be-all. This is the basics. It's going to take you a while I'm still learning. It's going to take you a while to understand more and more about quantum mechanics. But you'll like it. You'll enjoy it because actually as you understand it, it'll help. If you're receptive to the information, it's like anything else. Your personal life can be affected and changed for the good with understanding all of this. Understanding that thoughts create reality is a very... it's a positive thing if you know that you can, create more positive, more of a positive reality, not only for you but for everybody. Because you not only once you're doing it for yourself, you're also putting that out there, and everybody. And if everybody did that, then collectively, the world would be a better place, right? And people collectively put their fear out there, and look how effed up it is. So, I know. It's a lot of this is complicated, but it's important to understand all this stuff. It really is. And having a basic idea that science actually supports the idea that thoughts create reality, that's the measurement of the particle, that would be you thinking, right? I know, it's a much deeper level, but trust me, ladies and gentlemen, we're leveling the playing field, even if you don't realize it. We'll be right back. Don't go anywhere. All right, ladies and gentlemen, we are back. Final segment. I'm going to let the rest of the documentary play out without interrupting it as best I can, because I want to get the last few minutes in here, and then I will finish up with my final thoughts. Again, just quantum physics is cool. This is just a quick nutshell of some basics. It's much deeper. But now you have a more realistic understanding that science backs up the idea, the concept, the reality, I guess now that you could say, right? That thoughts do create a reality. Remember that. You create your own physical reality around you. So if you have negative, panicked, anxiety-driven thoughts, well, your life is going to reflect that. If you hate on yourself, it's going to reflect that. That's why I've told people before, look in the mirror and tell yourself you love you and that you're a good person. No matter how bad you've messed up in the past. As long as you really, in your heart, want to change and you want to be a good person and you want to do good, stop beating up on yourself and tell yourself that. Remember, thoughts create reality, and the science that you've heard tonight backs that up. And that's what quantum mechanics... I love when the physicists go, I can't explain how it works, but that's how it works. I love it. Science, spirituality, and I don't know, just the search for the answers to everything are all starting to finally merge and get along. And there's nothing wrong with that. All right, anyway, I'm going to let it finish up. I wound it back about a minute and a half, picking up with human teleportation. And remember the health aspects that I talked about, but I'm going to let it play out. Here you go.
But could this go even further? Since we're made of particles, could this process make human teleportation possible one day?
Welcome to New York City.
Let's say I want to get to Paris for a quick lunch. Well, in theory, entanglement might someday make that possible. Here's what I'd need. A chamber of particles here in New York that's entangled with another chamber of particles in Paris.
Right this way, Mr. Green.
I would step into a pod that acts sort of like a scanner or a fax machine. While the device scans the huge number of particles in my body, more particles than there are stars in the observable universe, it's jointly scanning the particles in the other chamber, and it creates a list that compares the quantum state of the two sets of particles. And here's where entanglement comes in. Because of spooky action at a distance, that list also reveals how the original state of my particles is related to the state of the particles in Paris. Next, the operator sends that list to Paris. There, they use the data to reconstruct the exact quantum state of every single one of my particles, and a new me materializes. It's not that the particles traveled from New York to Paris. It's that entanglement allows my quantum state to be extracted in New York and reconstituted in Paris, down to the last particle.
Bonjour, Monsieur Green.
Hi there. So, here I am in Paris, an exact replica of myself. And I'd better be, because measuring the quantum state of all my particles in New York has destroyed the original me.
It is absolutely required in the quantum teleportation protocol that the thing that is teleported is destroyed in the process. And, that does make you a little anxious. I guess you would just end up being a lump of neutrons, protons, and electrons. You wouldn't look too good.
Now, we are a long way from human teleportation today, but the possibility raises a question. Is the Brian Greene who arrives in Paris really me? Well, there should be no difference between the old me in New York and the new me here in Paris. And the reason is that, according to quantum mechanics, it's not the physical particles that make me me. It's the information those particles contain. And that information has been teleported exactly for all the trillions of particles that make up my body.
It is a very deep philosophical question whether what arrives at the receiving station is the original or not. My position is that by original we mean something which has all the properties of the original. And if this is the case, then it is the original.
I wouldn't step into that machine.
Whether or not human teleportation ever becomes a reality, the fuzzy uncertainty of quantum mechanics has all sorts of other potential applications. Here at MIT, Seth Lloyd is one of many researchers trying to harness quantum mechanics in powerful new ways.
Quantum mechanics is weird. That's just the way it is. So, life is dealing us weird lemons. Can we make some weird lemonade from this?
Lloyd's weird lemonade comes in the form of a quantum computer.
These are the guts of a quantum computer.
This gold and brass contraption might not look anything like your familiar laptop, but at its heart, it speaks the same language. Binary code. A computer language spelled out in zeros and ones, called bits.
So the smallest chunk of information is a bit. And what a computer does is simply busts up the information to the smallest chunks and then flips them really, really, really rapidly.
This quantum computer speaks in bits, but unlike a conventional bit, which at any moment can be either 0 or 1, a quantum bit is much more flexible.
Something here can be a bit. Here is 0, there is 1. That's a bit of information. So if you can have something that's here and there at the same time, then you have a quantum bit or qubit.
Just as an electron can be a fuzzy mixture of spinning clockwise and counterclockwise, a quantum bit can be a fuzzy mixture of being a 0 and a 1. And so a qubit can multitask.
Then it means you can do computations in ways that our classical brains could not have dreamed of.
In theory, quantum bits could be made from anything that acts in a quantum way, like an electron or an atom. Since quantum bits are so good at multitasking, if we can figure out how to get qubits to work together to solve problems, our computing power could explode exponentially. To get a feel for why a quantum computer would be so powerful, imagine being trapped in the middle of the hedge maze. What you'd want is to find a way out as fast as possible. The problem is there are so many options.
And by the way, quantum computing is what I've talked about when a couple weeks ago, last time I had Liam on, and we talked about, it was last week, and we were talking about AI, and I was talking about drones making a decision to kill people and then Terminator robots and everything else. Well, and he, one of his things about not worrying about it, at least right now, was, well, the technology isn't that advanced. Well, that's what quantum computing will kick into high gear. Just think about it.
And I just have to try them out, one at a time. That means I'm going to hit lots of dead ends, go down lots of blind alleys, and make lots of wrong turns before I finally get lucky and find the exit. And that's pretty much how today's computers solve problems. Though they do it very quickly, they only carry out one task at a time, just like I can only investigate one path at a time in the maze. But if I could try all the possibilities at once, it would be a different story. And that's kind of how quantum computing works. Since particles can, in a sense, be in many places at once, the computer could investigate a huge number of paths or solutions at the same time and find the correct one in a snap. Now, a maze like this only has a limited number of routes to explore, so a conventional computer could find the way out pretty quickly. But imagine a problem with millions or billions of variables, like predicting the weather far in advance. We might be able to forecast natural disasters like earthquakes or tornadoes. Solving that kind of problem right now would be impossible because it would take a ridiculously huge computer. But a quantum computer could get the job done with just a few hundred atoms. And so the brain of that computer, it would be smaller than a grain of sand. There's no doubt we're getting better and better at harnessing the power of the quantum world. And who knows where that could take us. But we can't forget that at the heart of this theory, which has given us so much, there is still a gaping hole. All the weirdness down at the quantum level at the scale of atoms and particles, where does the weirdness go? Why can things in the quantum world hover in a state of uncertainty, seemingly being partly here and partly there, while you and I, who after all are made of atoms and particles, seem to always be stuck in a single definite state? We are always either here or there. Niels Bohr offered no real explanation for why all the weird fuzziness of the quantum world seems to vanish as things increase in size.
As powerful and accurate as quantum mechanics has proven to be, scientists are still struggling to figure this out.
Some believe that there's some detail missing in the equations of quantum mechanics. And so, even though there are multiple possibilities in the tiny world, the missing details would adjust the numbers on our way up from atoms to objects in the big world so that
it would become clear that all but one of those possibilities disappear, resulting in a single certain outcome. Other physicists believe that all of the possibilities that exist in the quantum world, they never do go away. Instead, each and every possible outcome actually happens.
Only most of them happen in other universes.
Bam. Dimensional travel. What do you mean, Popeye? If there's other dimensions, that means you could travel to another dimension. If you've ever seen the show that it used to be on, I think, Fox, but it's canceled now. It was called Fringe. Part of their a lot of their writers must know a lot about quantum mechanics and old school science fiction writers and stuff, because a lot of the stuff is almost like based off of it or an homage to it. But part of their plot line was traveling in between. There were two universes, two timelines, if you will, and like in one timeline, which was our timeline here, the normal timeline that we all know, right? Normal 9/11 happened, the towers were attacked and blown to smithereens by whatever, we can debate 9/11 itself, but you know what I mean, the towers were attacked. In the alternate timeline, the towers still stood, because different decisions, different outcomes, right? Well, that's what this is saying too, that there's different dimensions, there's different possibilities, and it's not that just only one of those possibilities ends up becoming the outcome, and people go, well, then what the hell would make that, explain how that would work, how it narrows it down to that one possibility. Well, what happens if all those possibilities become a different reality somewhere, a different universe? That's why when you hear me talk about the universe, you'll hear me say the universe, and then you'll hear me say the word multiverse. I'm talking about other universes like this, other dimensional travel, whether it's a universe on the micro level, or what if we're the micro and there's something bigger in the macro. As above, so below, the law of correspondence. See how everything dovetails with each other, ladies and gentlemen? The occult, science, the quest for knowledge, everything I talk about on this broadcast. It's all one huge class. I'm really glad you all show up. Anyway, got a few minutes. Let me finish this.
Parallel to our own. It's a mind-blowing idea, but reality could go beyond the one universe we all see and be constantly branching off, creating new, alternative worlds where every possibility gets played out.
This is the frontier of quantum mechanics, and no one knows where it will lead.
The very fact that our reality is much grander than we thought, much more strange and mysterious than we thought, is to me also very beautiful and awe-inspiring.
The beauty of science is that it allows you to learn things which go beyond your wildest dreams. And quantum mechanics is the epitome of that.
After you learn quantum mechanics, you're never really the same again.
As strange as quantum mechanics may be, what's now clear is that there's no boundary between the worlds of the tiny and the big. Instead, these laws apply everywhere, and it's just that their weird features are most apparent when things are small. And so the discovery of quantum mechanics has revealed a reality, our reality, that's both shocking and thrilling,
bringing us that much closer to fully understanding the fabric of the cosmos.
Imagine that. Think for a second, ladies and gentlemen. Think about all the possibilities. I mean, obviously we've been lied to on so many levels, but just think. Imagine. They just told you that right now, quantum mechanics, and this is everything that we've talked about has now been proven up to where we are, is at this Wild West frontier, looking into the unknown. Multiple universes. I've heard about this before somewhere else. Something that people would probably call you kooky. Time travel. The theory of time travel is possible too when you start to look into quantum mechanics, because it's not so much that the way we view time isn't really time. And if everything, all these different possibilities, it gets really deep. I don't want to get too sidetracked on that. That's a whole nother broadcast because there's so much to go over. I'm actually working on getting a couple different scientists and stuff on the broadcast to talk more about this stuff and get more in depth. But the first thing I wanted to do was kind of break the barrier a little bit, break the ice, as it were, with quantum mechanics. And that was the goal of doing this tonight. It shows you that science backs up things that people like David Icke and others have said, I've said, because of my research that I've done, seeing some of Icke's research, but not just his, many others. Red Ice Creations does talks a lot about this stuff. Henrik does a lot of good interviews. Go check them out. But this all touches with the nature of reality. And when I say to you guys, choice, I was going with the Icke thing where he says that choice. Our thoughts create reality. They manifest reality. Well, now quantum physics is saying the same thing. I mean, obviously he used his research into the stuff that he did. He was exposed to quantum mechanics, and it shows that, yes, science does back up, his analysis of things to a certain degree, at least in that aspect. And hundreds of, thousands of other people have said the same thing. You just don't know about it. It's blocked. You're not told. You're American Idol's on. This is boring. You don't want to know about this. It's not cool to be a geek. It's not. It's not cool to be a geek. Go back. Go watch the Kardashians. No, it is cool to be a quote-unquote geek or nerd or whatever pejorative label they want to throw on it. In fact, I say we take the label and we run with it, and switch it up, right? Destroy it. Take it back from them. Now, you know what? It is cool if you're a nerd, or if you consider yourself to be a nerd because you like science or whatever. It is cool. Science is cool. I'm covered with tattoos, right? I've had motorcycles. Like I said, I was a firefighter. I was in the military. I kind of have, well, at least when I was younger, I kind of had a hankering for getting into brawls. But I'm a science geek. I'm a geek. Well, who cares? I'm a nerd. I'll admit it. And most people are. A lot of this stuff they don't understand it, and it makes them feel ignorant or inferior, and the ego kicks in. And that's where I don't care about this stupid stuff. Only nerds and geeks or dweebs care about this. No, actually, everybody should care about it, because it goes to show you how your reality is. And once you understand how reality really is, you can understand how your reality is being manipulated. Get it? Because you can bet your bippy that the powers that shouldn't be have an understanding of this. Okay? And having an understanding of how reality can be manipulated, you wonder why people go, I don't understand why, these idiots, they vote for the same people over and over and over again, and they put them back in office, even though they say they hate them. Well, when you can manipulate one's reality, And who knows what that individual, remember, quantum mechanics, there's all different possibilities, right? So the possibility of what that person is seeing, it gets really deep. But the point is you can manipulate reality on a mass level and even into one person's level. If you understand, it's like, think of it as I'm giving you access to the instruction manual and the equipment that only a certain amount of people or a certain, small group of people want to have and try to keep from the masses. I mean, you wonder why college is so expensive. You wonder why they make it. They make this stuff. I mean, the kids are dumbed down in school anyway. I'm sure if they taught quantum mechanics back, or at least the theories of it, the basics of it, in like a high school science class back in like the 50s or the 60s, those kids would have understood it. Nowadays, no. And I mean, maybe, who knows, maybe. And maybe they do. I don't. All I know is when I was in class, when I was in science, they didn't talk about this stuff. And the stuff that they did talk about was very textbook-oriented and controlled. And, it was all mind-numbing brainwashing. And they don't want you to understand how reality really is. Because if you understand at a basic level, if you understand the instruction manual to the game, right, then you're going to understand maybe how you're being screwed. And then maybe you because, look, I know I only taught you the science part of it tonight, and I didn't really teach you. I exposed you to the science part of it tonight, and only a little bit thereof. When you heard at the end when the one scientist said, he said, once you experience quantum mechanics, you're never the same once you kind of understand it. Well, it's the truth. Once you understand these things, you start to look at reality again. It's literally like seeing the matrix for what it really is. You're going to look at the world like Neo does. You're going to see everything in binary code. You're going to understand things a little differently. And what that does is just by having that basic understanding that things are a bit different than what you were taught and what you were programmed from the time you were younger, that makes you look at everything with a fresh set of eyes. And when you start to look at everything with a fresh set of eyes and you start to question things, then more and more things start to make sense and more puzzle pieces click. And then when you step back and you see, you can actually understand the picture for how big it really is. Because remember, when you start to wake up, it's always usually like an inch or two away from the picture, and you only see a small portion of it. You don't realize that if you step back, the painting's actually like 100 foot by 50 foot. In size. It's huge in dimensions, and you only see a couple inches of it when you're first, the nose right up on it. And then when you step back, initially the picture's really fuzzy and it doesn't make sense because there's a lot of pieces of the jigsaw picture. If it was like 100 foot by 50 foot, 100 by 50 foot jigsaw puzzle, and you didn't understand it, you were looking at it, you were, wow, this thing is kind of, there's a lot of pieces missing. Understanding this kind of thing, the nature of reality, or understanding that your reality is not what you have thought it really is. Even if you're in your 70s and you think, oh, what am I going to do? You'd be surprised. If you understand the rules, everything changes. Doesn't matter how old you are or how young you are. Understanding that having the rule book levels the playing field. Having a basic understanding of the rules levels the playing field more than not understanding that. And like I said, now when I say to you thoughts create reality, now you can see that quantum mechanics, science, is saying yes. Okay, when you watch the What the Bleep Do You Know movies, it'll get deeper into the whole thoughts create reality part of it, because it kind of helps merge that gap between a little bit somewhat between spirituality and science and everything else. And I mean, that's eventually going to happen. That's what happens as we get smarter. We're going to understand things a little bit better. And things that we clung to in the past, whether it be scientific beliefs, hardcore religious beliefs, whatever, they'll start to make sense a little bit more because they'll start to merge together. And the opposition to each it'll just go away, because eventually you'll realize that both sides are right. They were coming at it from a different aspect. But if you look at it, if you put them both together, it understands things a little bit better. Like I said, thoughts create reality. So If you start beating up on yourself, start looking at yourself in the mirror every day and, oh, you're a shitbag, well, guess how you're going to feel. So look at yourself in the mirror, tell yourself you love yourself, tell yourself you're a good person, you forgive yourself for your past transgressions, and move on.
This is Sparta!
It's a small start, but it's a start. All right, ladies and gentlemen, class dismissed. We're out of here for the weekend. I'll catch you all again Tuesday night. Till then, as I say, the solutions to our problems are an inside job. Have a good weekend. Be safe. I love you all. And keep checking out quantum mechanics. I'm out of here.